In R2, the length of a vector v equals v1, v2 can be found using the Pythagorean theorem. So this is just the square root of v1 squared plus v2 squared. So visually, if I have some axes here, and I have my vector here, well, the length, you just drop over here, look at the components. This is a right triangle. So v1, v2, and its length is the square root of v1 squared plus v2 squared. We can generalize this to R3 and R4 and higher by noticing that v1 squared plus v2 squared, this is exactly v dotted with itself. So in other words, this length here is the same as the square root of v dotted with v. That brings us to the definition of the length of a vector. The length of a vector, also called the norm or magnitude, of a vector. You spell that right, not a V at the end. Vector. Length of a vector. I don't have a period there. The length of a vector V is written with these double vertical bars, and it is the square root of v dotted with itself, and when you write that out, it's the square root of v1 squared plus dot 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 plus vn squared. So for instance, the norm of the vector 1, 2, 3, 4 is, well, it's the square root of 1 squared plus 2 squared plus 3 squared plus 4 squared, which, when you compute this all out, is going to be the square root of 30. I also want you to notice that the norm of c times v is the absolute value of c times the norm of v. The next thing I want to talk about having to do with length, let me move everything up here, is unit vectors. A unit vector is a vector with length 1. In R2, the collection of all unit vectors forms a circle. For instance, 1, 0, 0, 1, minus 1 over the square root of 2, comma, 1 over the square root of 2, and many others. We have certain things called the standard unit vectors, and that's these first two, E1 and E2. So E1 is this guy, and E2 is this guy. These are called the standard unit vectors in R2. We have standard unit vectors in Rn. So the standard unit vectors in Rn are the vectors E1 equals 1, 0, 0, dot, dot, dot. E2 equals 0, 1, 0, dot, dot, dot. E3 equals 0, 0. Equals 0, 0, 1, dot, 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 and so on. Finally, if v is not 0, is not the 0 vector, we can turn v into a unit vector by dividing by its length. We call the vector we get v over the length of v is the normalizing vector of v. We can also use the dot product to talk about distance. If we think of the vectors u and v as starting from the origin, which is what we usually do, then we can define the distance between their tips, which we for shorthand just say the distance between u and v. We define that to be d of u v is the length of the vector u minus v. So for instance, the distance between 10, 10, 10, 10 and 11, 11, 11, 11 is the length of the difference between these two is negative 1, negative 1, negative 1, negative 1, which is the square root of 4, which is 2. And now we come to a theorem! Yay! This is called the triangle inequality. Let's kind of think about what does this mean visually. Well, it's telling us that if we have a vector u and a vector v, well then when we add them, we get this vector u plus v, that the sum of these two guys, of their sum of their lengths, is bigger than the length of this guy. In other words, traveling first along u, then along v, we've traveled farther than if we just traveled along u plus v. So this is geometrically plausible. And we can prove this in a few different ways. The book proves this using theorem 1.4. I'm just going to leave us with this geometric intuition. Let's just double check this with an example. We can look at the vectors u equals 1, 0, and v equals 3, 4. U plus v in this instance is going to then be 4, 4, and the length of u plus v is going to be the square root of 16 plus 16, which is the square root of 32, which, if you put into a calculator, it's approximately 5.7. On the other hand, the length of u plus the length of v is 1 plus 5, which is 6. And certainly 6 is greater than, or equal to, it's greater than 5.7.